Alright, folks, we're going to try this today, and it might be a little weird because I'm filming this during my hypothetical office hour, which should be taking place starting in 3 minutes. So, depending on how many people show up or want to talk, then I may have to pause or delete this all together. But I thought, what the heck, I'm probably going to sit here by my own for a little bit. Let's go ahead and do a little more lecturing done. So, now we are going to talk about the aldol reaction and the aldol condensation. Now, both of these can occur kind of at the same time, and while they can use both the acid or base pathways, for some reason, the base pathway seems to be preferred in almost every example of us doing these. All right, so what is an aldol? Valid question. An aldol is one of these weird pieces of Franken nomenclature that you can piece together on your own. An aldol is a molecule that would look like this. ALD of aldol comes from this aldehyde. The OL of aldol comes from the alcohol here. So, kind of like enamine, this one actually starts to make sense in terms of the name. Now, the aldol reaction and the aldol condensation are fundamentally different reactions, but the aldol reaction has to come first. So let's take a look at how this works using a base-mediated pathway to start with. We are going to start with this aldehyde, propanaldehyde. And what we're going to do first is apply a base. Now, I know I've gone on about the right bases to use and pKa and all that stuff. Honestly, the way the equilibrium lies, you could use almost any base here. So, in point of fact, I'm going to bring, once again to the table, sodium hydride because I know it'll do its job. You could use sodium hydroxide here. You could use LDA. You could probably use ethoxide and get the same thing accomplished. Either way, though, the first piece of this is you are going to deprotonate that carbon. You're going to deprotonate that alpha carbon to the carbonyl. Why? Because there's a very nice resonance structure that forms when you do so. Now, once again, remember, I prefer this structure of the enolate. Your book prefers the anion on the carbon. Neither one is technically wrong. Both are acceptable. All right, now, if I had bromine, at this point, I would add the bromine and we would brominate off that side. If I had a primary alkyl halide, we could alkylate off that side. But the fact of the matter is, I don't have any other electrophile in this system. Or do I? Do I have another electrophile in this system? Yes, ladies and gentlemen, I absolutely do. And it would be an unenolated, I don't know if that's a verb, I just made it one, an unenolated aldehyde. So, we have our electrophile built in here. So, the electrophile would look like this, or rather the mechanism. Reform the carbon-oxygen pi bond, have the pi bond that was in the carbon-carbon, electrons from the carbon-carbon pi bond, nucleophilically attack the carbonyl carbon, and open up. So now we've got this. All right, now we've got that structure. And we're almost home. What we can do is protonate that oxygen with a little bit of water that we could have in system, and we would get here. Now, for those of you who are really astute and playing along at home and wondering where did that water come from if he used sodium hydride at the beginning, that's what we call a mistake-o, or a right-o in this case. We could very easily say 1 sodium hydride, 2 water, and we'd accomplish the same thing. Did I cheat a little bit there? Yes, but it's my class. If I can't cheat a little bit, what's the point of having fun? Okay, now aldols work best. Aldol formation works best with 1 aldehyde, like we just saw, where the aldehyde that from the enolate and the electrophile are one and the same. You can get crossed aldol reactions. Honestly, crossed aldol reactions are a great invitation for chaos. Let's say that we have these 2 ketones. Now, I know aldol very specifically has aldehyde in the name. Ketones work just as well, and it's not necessarily called a ketol. It's still called an aldol. So let's say you have an even mix of these 2 ketones, acetone and acetophenone. We've got a 50-50 mixture of both of these with, let's say KOH and water for our bases. What I want you to do is hit pause and then figure out the number of different aldol products you would get from this. I'll give you one hint: only work from one side of the acetone. You don't have to work from the other side too. I want you to figure out the total number of aldol products you would get out of this and their structures. I'll give you a couple minutes to work on it. I'll be right back. Hey, I'm back. You're still here, so let's take a look at that. Remember, our 2 ketones we could have started from included acetone and acetophenone. Both of these 50-50 mix with KOH in water. Rather than frog march through the mechanism for these, well, I will for the first one because I think it's a valuable thing. There's a certain learning advantage that comes with repetition, even though you may find it boring and pointless. And to be honest with you, it probably is boring and pointless. But sometimes just sheer repetition can really help things stick in your brain. So we form the enolate, and we're going to react it with another ketone, like so. Open that up. Add the proton, and we get this. So we're going to call this one, if we call this ketone A, this is AA. If we call acetophenone here ketone B, then the mechanism would look like this. Whoops, didn't need to do that. We'll erase that. And we are going to proceed over here. To this enolate. To this ketone. Bang, bang, bang. Pick up a proton. And what we make is this. And this would be the BB ketone. Now, I'm running out of time. So, next page, I'm just going to show you the other two aldols. All right, so next page. Here are the other two aldols. Just let me check my colors real quick. And here we go. This would be the aldol formed from reacting acetone as the enolate and acetophenone as the electrophile. And this one would be formed using acetophenone as the electrophile and acetone as the acetophenone as the enolate and acetone as the electrophile. These can also be done through acid pathways. So here's what I want you to work on for now, and then we'll start the next video. That shut off at some point, and I apologize. Hopefully this isn't too much of a shock. What I'd like you to do for the next problem is this. Take a look at this reaction in blue. I want you to show me the acid-catalyzed pathway of transforming acetophenone into the aldol product. Again, note we are using acid here, not base. So it is enol, not enolate. Take a stab at that, and I'll see you in a few.